Okay, so once again, I am working off the guided notes from Chapter 7. I have a copy of the notes up on my screen, as well as the visual of this lovely grid paper that you see. What you guys are seeing is likely just the grid paper in Blackboard. However, if you go to this file, once it's visible on the YouTube channel, on my YouTube channel, then you will be able to see both the note page and both this note page and the guided notes. All right, so we're still in probability in Chapter 7. Today, the goal is to do section 7.6 and section 7.7. So 7.6, we're going to cover events involving not or and odds. So those are the three topics we're covering in section 7.6. Where's my blue? Let's see how my pen does. All of my pens are dying, like all of them. Okay, so one of the first things to understand is the idea of complements. Complements are the probability that an event will occur taken with the probability it will not. So taken with the probability the event will not occur. These two events together, the event that something will happen and the event that it will not, are called complements. So, an interesting thing happens. The probability of an event added to the probability that the event will not occur always adds up to 1. Now, we have to be careful about this because it's the probability that an event occurs and the probability that it doesn't occur. Hey, Cole. Welcome. All right, we're good. Okay, so we get from this particular makeup 2 smaller pieces of information. The probability that an event occurred can be thought of as 1 minus the probability that the event does not occur. Or we can say the probability an event does not occur has to be 1 minus the probability that that event does occur. So these are essentially just rearranging this idea and sort of turning it around a little bit. Okay. All right, what do I got here? 1, 2, 3, 4, 5, 6. So on the page, I actually have these as marbles, but I don't really have marbles here. I'm just going to color in the blocks. Okay. So let's take a look at this in a simplistic manner. Problem number 1 says, what is the probability of choosing a yellow marble or a yellow brick? I can get the probability of yellow by looking at my choices and seeing that there are 2 yellows out of 12. This gives me a probability of 1/6. Now, the probability of not yellow. Interesting notation. This lovely little tilde means not. There are other notations for a not, but just know we don't always write it out. So I can do this one of 2 ways. I can count up all of the blocks that are not yellow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 12, which will reduce to 5, 6. Or I can recognize that this should be the same as 1 minus the probability of the yellow. Since I already found probability of yellow, I can do 1 minus 1/6, which is still going to give me 5/6. Honestly, for a sample as small as 12, when there are as little as 12 outcomes, we tend just to count them up because it's just as fast. But if I had 250 outcomes, I might find it faster to do 1 minus than I would to count up all the options that are not. For example, if I go to the probability of not pink, I can count up all the pinks. That's quick. So I might choose to do 1 minus the probability of a pink, which would be 1 minus 3/12. And I would bet that several of you would just pull your calculator out, use your fraction button, 1 minus 3/12, to get an answer of 3/4. The probability of not blue. I can count up those that are not blue, or I can do 1 minus the probability of blue. So 1 minus 6/12, which is going to be another 6/12, or 1/2. Questions there? Okay. All right. To give it a little bit more, oh, this was 3. Okay. All right, so now we're going to go back to a standard deck of cards as we did from Tuesday. Oh, sorry. Find the probability of not a queen. Well, how many queens are there? So I could do 1 minus 4 out of 52. Since I knew real quick that there were 4 queens, I might find it faster to do 1 minus 4 of 52, which is 12/13. What's the probability that you are not dealt a red 7? This would be the same as 1 minus the probability of a red 7, or 1 minus 2 out of 52. 25, 26. Okay. This rears its head most when we're dealing with pie charts. I don't know if you can see the pie chart. So I've got this pie chart in front of me, and it is got a lot of options here. Oops. Okay. And in this, we're asked to use the pie chart to answer the following. Determine the probability of a random driver is not in the 20 to 29 age. Well, the problem is that I've got 1, 2, 3, 4, 5, 6, 7, 8 different age groups. Yep, 2, 3, 4, 5, 6, 7, 8. Only one of those is 20 to 29. So the probability of not being in 20 to 29 is going to be 1 minus the probability that it is in 20 to 29. Or 1 minus 33 million out of, I still need the total. It's 42, 82, 122, 153, 172, 185, 191 million. Whew. So 1 minus 33 out of 191 million. Or about 82.7%. So approximately 83% of the people are not between the ages of 20 and 29. Right? Good. All right, so the next bit is stop. Okay. Gotta go back. Gotta go back. Execution window. Still. Okay. Sorry, it went away. There we go. All right, so the second piece out of 7.6 is mutually exclusive events and or probabilities. Here's our pieces of information here. If two events cannot occur at the same time, they are mutually exclusive. Okay, for example, I cannot sit at my kitchen table in Wisconsin and be on the beach in the Bahamas at the same time. These are mutually exclusive events. You cannot be at work and be sleeping at the same time. Well, maybe you can. Anyway, events that cannot occur at the same time are known as mutually exclusive. Okay, so to find the probability, of an or event, we use the following formula. The probability of A or B occurring is equal to the probability of A added to the probability of B for mutually exclusive events. So let's take, for example, a standard deck of cards. What is the probability of choosing a jack or a queen? Shoot. First, let's be clear. Can a card in a deck of cards be both a jack and a queen? Can one card, just one card, be a jack and a queen at the same time? You're right. In a deck of cards, it's either a jack or a queen. It cannot be both. That's what makes it mutually exclusive. since a card could not be both a jack and a queen at the same time, they are mutually exclusive. So the probability of a jack or a queen is the same as the probability of the jack plus the probability of the queen. When it comes to jacks, there are 4 out of 52. When it comes to queens, there are 4 out of 52. This is a total of 8 out of 52, which will reduce to 2/13. If we were to use a standard 6-sided die, what is the probability of rolling a 4 or a 5? Just to be clear, when you roll a die, can you get both a 4 and a 5 at the same time? You're only rolling one die, right? I can do it if I'm rolling 2 die, that's a different situation. But if I'm only rolling 1 die, it's either got to be a 4 or it's got to be a 5. I can't get both at the same time. So these are mutually exclusive events. And I have the probability of a 4 added to the probability of a 5. Or 1/6 plus 1/6, which is 2/6 or 1/3. Okay. Now, not all events are mutually exclusive. Sometimes there is overlap. So then we got to look at ORs. Or events when they are not mutually exclusive. Okay, so non-mutually exclusive events essentially means that the two events have some overlap. They can happen together, even if they don't all the time. For example, when you're sitting at your kitchen table, are you wearing a hoodie? These are two very separate things. You can sit at your kitchen table and you can wear a hoodie. You sometimes do them together, but not always, right? Just because you're sitting at the kitchen table doesn't mean you're wearing a hooded sweatshirt. And just because so there's overlap, okay? So if A and B are not mutually exclusive, then it has to be true that the probability of A or B will start out the same. It's the probability of A added to the probability of B, but we have to subtract the probability that they're happening at the same time. Okay. So let's try our deck of cards again. So we're going to start with a standard deck of cards. And we want to know the probability that we draw a heart or a 7. Some of the cards will be hearts. Some of the cards will be 7s. Are there any cards that are both a 7 and a heart? Right? There's a card that is called the 7 of hearts. It is both. So these two probabilities are not mutually exclusive. I can find the probability of a heart. I can add that to the probability of a 7, but I have to subtract the probability of a 7 of hearts. Why do I have to subtract this? Well, actually, because it was counted twice. I counted the 7 of hearts when I counted up all the hearts. And I counted it a second time when I counted up all the 7s. So that means this 7 of heart was actually counted twice. So I need to take it away one time because I counted it one extra time. There are 13 hearts out of 52 cards. There are 4 7s out of the 52 cards. And only one card out of the 52 is a 7 of hearts. So that's 13 52s plus 4 52s. That's 17. Minus 1 gives me 16 out of 52, which will reduce to, I think, 4 13ths. Am I right? Yep, 4 13ths. Given a standard die, what's the probability that you roll an even number or a number less than 4? So, are there even numbers that are less than 4? Okay, so we're going to find the probability of an even. We're going to add that to the probability of a number smaller than 4. And we're going to subtract the probability of an even less than 2. So, yeah. Oh, no, this is a dice. Yep. Yep. So even would be 2, 4, 6. That's 3 of them. Less than 4 would be 1, 2, 3. So that's another 3 out of 6. Minus even numbers less than 4 would be 1 out of. So we're going to get a 5 out of 6. All right. Questions so far? It's all right. I'm not moving anything yet. Is that what you need, Lex? Okay. All right. I'm going to try a problem with a slightly different bent, but the same kind of thing. I'm going to jump to number 15. And for problem number 15, we actually have a table again. We've got male, female, and total. And then we're comparing married, never married, what else we got? Divorced, beheaded, no, widowed. And then they put a total over there too. Okay. All right, so of the males, 65 were married. Of the females, 65 were married, giving us a total of 130. 40 males never married, 34 females never married, giving us a total of 74. Of the divorced, 10 of the males were divorced, 14 of the females were divorced, giving us 24 total divorced people. Of the widowed, 3 were male, 11 were female, giving us 14 total widowed. If I add them up in the rows, I have a total of 118 men and 124 women, giving me a grand total of 242 people in this particular questionnaire. Whatever. Now, part A says, what is the probability that the person is divorced or male? This is an or problem. That means that I have to consider each probability. So the probability of divorced added to the probability of male, but then I must subtract anyone who falls into both categories. So the probability of divorced and male. All right. So how many people were divorced? Out of 242. Add that to how many people were male? Nope. Yep, we want the total. Just male would be the total male or the 118 out of 242. And now we want to take away the people we counted twice. That is those that were already divorced and male. So there's where we're going to use our 10 out of 242. 24 plus 118 minus 10 is, I think, going to give me 132 out of 242. Or 6/11. right? The second probability asks us to find the probability that the person is married or divorced. Well, this is an or problem, so I can immediately set it up as the probability of married added to the probability of divorced, and then I can subtract anybody that's both. But what's the problem with being both married and divorced? Can you be both married and divorced at the same time? I mean, you can have a previous divorce and be remarried, but now you're married, right? So sometimes you'll set it up and this overlap just doesn't happen. So we cross it out. That means what you had were mutually exclusive events. So married is 130 out of 242. Divorced is 24 out of the 242. $154 out of 242. Whoops. 7/11. Nice. Yep, that's what I got, Cole. Oh, scooch. Or you could just put it in as a 0. Correct. It's just not possible. All right. Moving right along. Ch-ch-chung, ch-ch-chung. But loose and fancy free. No, that's bad. The last part of 7.6 is about odds. All right. I got a lot to say about odds. Odds are pretty easy. However, odds are very close to probability. And most people in normal daily regular life consider odds and probability to be the same thing. They are not. Mathematically, they are different comparisons. Odds in favor compares the probability of an event to the probability that the event does not occur. Odds against takes the probability that an event does not occur and it compares it to the probability that the event does occur. Part of the confusion here is that we use probability to find odds, but odds and probability are not the same thing. I'm going to go off script for just a minute here. And I'm going to go back to our wonderful little bricks or balls or whatever you want to call them. All right. If I am asking you to find the odds in favor of yellow, I want you to compare the probability of getting a yellow to the probability of not yellow. So how many yellows are there here? So the probability of yellow would be 2 out of 12. The not yellow would then be 10 out of 12. The odds in favor of yellow are 2 to 10, which reduces to be 1 to 5. The odds against yellow we're asking to find the probability of not yellow in comparison to the probability of yellow. Do you see how it's just the flip? So I'm going to get 10 to 2, which will reduce to be 5 to 1. You what? No, I said I was going off script. This one is not in your pack. I just tried to find a slightly easier example to start with. All right. Now, do you notice that when we do the probability, it's 2 out of 12 and 10 out of 12, but we really only need the 2 and 10, as in 2 are yellow, 10 are not yellow, and then that reduces to 1 over 5. And then the odds against ends up being just the flip. Yeah, so where the odds in favor were 1 to 5, that means the odds against are going to be the flip of that, or 5 to 1. So if we're looking at the odds against pink, because it's against pink, we're going to compare those that are not pink to those that are pink. Well, 3 are pink. 2, 3, 4, 5, 6. 9 are not. So this is 9 to 3, which when reduced will be 3 to 1. I need to have both numbers there, even though that reduces, because odds are ratios, meaning I need two numbers for comparison. So now if somebody asks me for the odds in favor of pink, if I know the odds against are 3 to 1, then the odds in favor are going to be 1 to 3. Questions? Stacy, you good with this? And Lexi? Correct. Now, yeah, most people, I mean, you could write this in fraction form too, but I reserve the fraction form for probability and I use the colon for odds, even though they can mean the same thing, just so I keep it straight. Like when I see myself writing in colons, I know I'm using odds. Yeah, I've just trained myself to do it a little differently, I guess. Okay, so let's try a couple. So if we're rolling a die, let's look at number 16 from the packet then. What are the odds in favor of a 6? One is true, because that's how many 6s there are. Yep. One is a 6, 5, or not. So the odds in favor of a 6 are 1 to 5. And you see how easy it is to give 1 to 6, Cole, right? Yeah. Yep. And you will forget. You will catch yourself when you're doing this homework. You will catch yourself often. It's just where our brain goes. Odds against, yeah, you can only land on one at a time, right? So one of those is going to be a 6. Five of those events or opportunities are not. So the odds in favor of a 6 are 1 to 5. Okay, let's try this one. What are the odds against an even numbered roll? So if it's odds against an even, we're going to compare the opportunities that are not even to those that will be even. So when you roll a die, how many of those sides are not even? There's 6 sides. Yeah, 6 sides on a die. 3 of them are not even. How many of them are even? 3. Yep. So this means that the odds against an even number are 3 to 3, which would reduce to be 1 to 1. This essentially says for every odd number, you could match it exactly with an even number. And let's consider a standard deck of cards. Odds in favor of a heart. There are 13 hearts. How many are? Then we would have 52 minus 13, or 13 to 39. Would this reduce? It does, but if you're not sure, use your calculator and your fraction button, 13, 39. So in a standard deck of cards, the odds in favor of a heart are 1 to 3. Oops. Odds against the 9. $48 would come first because it's against. So we want the losers first. Yep. So that would be 12 to 1. Okay? It's not always the little number, it's the winner of that event. Yeah. Yeah. So if it's in favor of that event, then that event comes first. And if it's against, you would put it last. Mm-hmm. Yep, good. Okay. What do I got? I don't have as much time left as I kind of want, so we're going to do a slightly abbreviated version of 7.7. All right, section 7.7 has two different types of probability. The two that we want to talk about are and probability, and then what's known as conditional probability. So probability involving and is some of my favorites. Okay. If A and B are independent events, then the probability that A occurs and B occurs, is equal to the product of those two. So I can multiply those two probabilities together. these are the same marbles and or blocks from before. The first thing we're going to look at is with replacement. With replacement means once chosen, it is put back. So, determine the probability that you choose a yellow and then a blue. Since these are independent events, meaning choosing a yellow one and choosing a blue one are two distinct outcomes, then what we can say is that this is equal to the probability of choosing a yellow multiplied by the probability of choosing a blue. Remember, it's with replacement. So we're going to choose a yellow. That's 2 out of 12. Assuming we win and we get a yellow one, we're just going to look at it and then throw it back into the grouping again. So when I choose a blue one, there are 6 blue ones. It is still out of 12 because I did it with replacement. Now all I have to do is multiply these probabilities together. 2/12 times 6/12, and we get 1/12. Questions? With replacement, yes, your denominator will always stay the same. Lexi? Lexi, did you have a question as well? It would be 12 over 144. Correct. Correct. And I prefer to pull it out of the calculator so that the calculator does all that reducing for me. All right, so what if we wanted to get blue twice? In other words, blue, then blue again. So it'd be the probability of blue times the probability of blue again, if I'm writing it all out, right? So that's 6 out of 12. And then blue again would be another 6 out of 12. We should get 1/4 with that. Okay. All right, so we're going to go back to the 10 question test. All are multiple choice. 4 answers each. Mal is just random guessing. So they do not know anything. Determine the probability that they get them all correct. Yes, it's 10 questions. Okay, well, there are 10 questions, yes. So the probability of getting one correct. So the probability that the first one is correct is going to be 1 out of 4, right? What's the probability that they get the second correct? That's 1 out of 4 again. And the probability that he gets the third correct? We're talking about all 10. So we're looking at the probability that he gets the first correct and the second correct and the third. Do you see all my ands? And the fourth. And we're going to keep going until we get to the 10th. So if I use this rule from above, the probability of A and B is the probability of A times the probability of B. Well, this is going to be 1/4 for the first, 1/4 for the second, 1/4 for the third. It's going to be 1/4 for each of these 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is going to be 1/4 to the 10th power because I got 10 questions. So I'm going to use my calculator and do 1/4 to the 10th. Yeah. Even if I multiply this to get a percent, what does this mean? Yeah. So if Mal says he entirely guessed and got 100%, I'm going to say he lied. Right? The chances of that happening are basically non-existent. It's not 0, but it's awfully close. Now, what's the probability that he gets them all wrong? Can you just subtract this from 1? Is that the alternative? Do you get them either all right or all wrong, or is there a middle ground? So if I were to say to you, Cole, I took a test, I didn't get them all right, does that automatically mean I got them all wrong? Right. So I can't just subtract this from 1. There is some middle ground. But the probability that I got the first one wrong would be what? Well, there's 3 wrong answers out of 4. So the probability of getting them all wrong would mean I got the first one wrong and the second one wrong. So that would be 3/4 to the 10th power. And that's going to be a 0.056 or about 5.6%. So if Mal said he entirely guessed and he got them all right, he's got to be lying because that's almost 0. If he said he totally guessed and he got them all wrong, well, that's a larger chance. He might not be lying, but that's really bad luck. Because there's a 5% chance he got them all wrong. Everything else is in the middle. That's where your gray area is. You got 2 wrong, you got 8 wrong. All of those are counted in the middle to these 2 extremes. You good? Okay. What do I got for time? Oh, man. Okay. Woo! You know what I should do? Hold on. Now. Okay. Oh, I'm getting a marker on myself. All right, I'm going to jump to conditional. All right. Conditional probability is the probability of an event occurring while giving a set of conditions that narrows the sample space. So the probability of event B assuming A has already occurred. It is written as or noted as the probability of B, I didn't want an A there, given A. probability of B given A is the probability that both A and B have occurred, given A has already. Given a standard deck of cards, what is the probability that you draw a heart given you're only looking at red cards? So we want to look at the probability that you're looking at heart and red compared to the probability of red. So how many cards are hearts and red? Well, hearts and reds. Well, there's 13 hearts that are also red. Now, how many cards are red? So the probability of getting a heart, given you're only looking at red cards. So even though we started with 52 cards in a deck, we're now only looking at the red ones. So there's only 26 of them. So we've narrowed our choices already. Of those 26, 13 are hearts. So this would be 13 out of 26, or 1/2. What is the probability of choosing a jack, given you're only looking at face cards? So we're going to look at the jacks and the faces. So cards that are both jacks and face cards. And then our denominator is only going to include those with a face. So there are 4 cards that are jacks and have faces, because all of our jacks have faces. And there are 12 cards with faces. So this would be 4 out of 12, or 1/3. Questions? Okay. All right, where am I on time? 6 minutes. All right. 15 uses the same chart from the previous page. I don't know if I want to. Can you guys look up so I don't have to repeat it? Can you, yeah, if you wrote it down in your notes, we're going to use this chart again. All right, so we want to find so we're looking at the married divorced chart from before. Okay. What is the probability that a person is divorced? Out of? Yep. So this is just a basic probability. The probability of being divorced is 24 out of 242, or 12 out of 121, if we're reducing. What is the probability the person is a divorced female? Now, this is saying both at the same time. We want someone who is divorced and who is female. And that would be 14 out of, yep, it would have to be out of the total of everyone. They meet both conditions, divorced and female. That's 14 out of 242, which is 7 out of 120. What's the probability a divorced person was chosen given that they are female? So now we're going to look up divorced and female. That's the same 14, but we don't want to compare them to the entire population. We just to the female population. The second notation here is what's going to go on the bottom, 124. For this problem, so the probability that they're divorced given that they're female means I'm only looking at the female row. So I want to take it out of the 124. I can switch it up if I ask for the probability that they're female, given I already know they're divorced. Now, because the given is the divorced bit, I'm only looking at that column now. I'm reducing my data to just the divorced people. So this is going to be out of 24. The females and divorced are 14. Correct. And I know we're focusing on the divorced because we're given that they're divorced. What's the probability of a female? All right, there was a lot. I probably should have done a little bit more on Tuesday, but oh well. It is what it is. Stacy, did I answer any of your questions? Okay, good. Good. I'm glad I snuck this bit in there then. Okay, good. I'm glad you got it then.